Welcome back to Chemistry 4300. In this video, we're going to begin Chapter 4, which is on the physics of rotational motion. Now what we're going to do is we're going to look at a collection of particles, but now this collection of particles is going to be constrained so that the relative positions of the particles in the system are going to be held constant. In other words, imagine I had some kind of massless rods that were holding these particles into their positions so that the shape of the object remained constant as the object moved through space and tumbled and rotated and whatever happened to it, this collection would always maintain its same shape. This is what we call rigid body approximation. We know that real objects, as they're rotating through space, will start to deform if they undergo too fast of a rotation, for example. But in this case, we're going to assume that that doesn't happen. Now, we'll also use this to describe molecules, and we assume that a molecule, as it's rotating, will eventually start having the bond stretching and the shape changing. But as a good approximation, we can describe all of these systems as rigid, and then any slight deformation, we'll be able to sort of make a correction to our approach that we're learning here, and everything will still be good. I mean, if the deformations become too dramatic, then the rigid body approximation breaks down, and then you have to do something else. Now, before we get started, we need to figure out how we're going to describe the orientation of our rigid body. And to help us with that, Euler has given us the rotation theorem, which tells us that effectively we only need 3 angles to specify the orientation of a body. So, for example, in this picture here, I've drawn some arbitrary shaped object, looks like kind of like a pear, and according to Euler, we only need 3 angles to specify the reorientation of this object to some new orientation. So here we define 2 angles. Theta and phi are used to define an axis, and then we will then rotate the body about that axis by an angle chi. And what's important about this definition, of course, is that this particular way we define it is the convention that we use in chemistry and physics, but other people have other definitions on how they define their Euler angles. So be careful when you're working with Euler angles that you're using the consistent definition throughout your calculations. But in this class, we'll try to be consistent. We should be consistent in using this definition. Now, one other thing I want to point out is that the sign of chi's is determined by the right-hand rule, which is that you put your thumb along the direction of the vector and your fingers should curl in the direction of positive chi. Now, another example, just also to illustrate the concept, but also show you that there are many other conventions in the field of aviation. They use Euler angles too, except they call them pitch, roll, and yaw. And so when you're describing the orientation of a plane, you would use the roll axis to describe how you would rotate about this axis or to move the wings down this way or that way. And then the pitch axis would be used to lift the nose or lower the nose of the plane. And then the yaw axis would be for what you would use to turn left or right. So those are 3 Euler angles that you use to specify the orientation. But we're not using that particular convention. We're using the one on the previous slide. Now, another important concept is the angular velocity vector. Now, you're used to the concept of angular velocity. So when you're driving down the road, you know your cars are rotating with a certain angular velocity. But what we're going to define here is something called an angular velocity vector. And so what we're going to do is we're going to define a unit vector that's along the axis about which we're rotating. And then we're going to multiply that unit vector times the speed at which we're rotating, or the angular velocity. And that's going to give us a vector quantity who points along the direction at which we're rotating, and the length of the vector is related, or gives us the speed at which we are rotating. So you imagine on your car then, that vector will be pointing along the axle of your car, and the length of it will be how fast the tire is rotating. In terms of Euler angles, we can define this unit vector along R using the angles theta and phi with this definition, using the Cartesian unit vectors there. And then the omega, the speed of the angular velocity is going to be the derivative of chi with respect to time. And again, the right-hand rule is in play here, so when you're looking at something, an object that's rotating, curl your fingers in the direction of the rotation, and your thumb will be pointing along the angular velocity vector. Now, when objects are rotating, you might expect that there's a velocity vector pointing along a certain direction as the object rotates about that direction. We'll see as we look at the physics of rigid bodies that that vector may not stay constant in time. It may start to move around. So just be aware that we're going to be describing angular velocities that are instantaneous. They're pointing at this moment here, but later as the object evolves in time, that angular velocity vector will be moving or could be moving in time. It's also important to be clear about how you define the origin when you're defining your angular velocity vector. So in some situations, it's pretty clear what the natural choice would be. For example, when you have a molecule, most of the time we're going to be wanting to set the origin for the angular velocity vector as the center mass of the molecule. Another example, just to show you a different case, is if you had a spinning top and you're describing the motion here, you wouldn't want to put the origin at the center of mass of the object, but you'd want to put it here at the tip of the top, where that is the origin that you're setting up your angular velocity vector in your coordinate system. Next, what we're interested in is going to be the relationship between the angular momentum vector and the angular velocity vector. So those two vectors are going to be related, and those are going to be two important vectors we're going to need to know as we describe the motion of our rigid body. And we're going to derive the relationship between these two guys here in the next couple slides. So let's look through this, go through this slowly and carefully to see how this is done. So first of all, we're going to define the total angular momentum of our rigid body with the symbol J. This is just a change in convention because in the physics of rigid bodies, we always use capital J for the total angular momentum and separate that from L, which we tend to want to use for other purposes. And when they end up getting mixed, we don't want to be confused about which one, total angular momentum we're working with. So whenever we're working with rigid bodies, we're going to use J for the total angular momentum. It's just a letter change, nothing more than that. So with that definition then, J is going to be equal to, for our system of particles, r cross p, and of course p is just the mass times the linear velocity vector. So I do a little rearranging, and so what we're worried about now is r cross the linear velocity vector. And for a particle in our rigid body, the linear velocity vector is going to be, for that particle, omega cross r, where r is the position vector for that particle. So in the rigid body, all of the particles in the rigid body will be experiencing the same omega, but they'll have different positions, so the linear velocity will be different for every particle. So I can take this expression and I can plug it in here, and I'll get this expression here. Now this is a cross product twice, or a triple cross product. So it's the cross product of r with omega and that with r again. So this triple cross product is something that can be a little tricky to work with, but we can do a little simplification here. And we can use an identity for the triple cross product, which is that if you have A cross B cross C, that you can rewrite that as A dot B, which makes a scalar, times a B vector, so we get B vector scaled by the scalar quantity, minus A dot B, another scalar, which multiplies the C vector, so scaling that vector, and the difference between those two is the result of this triple cross product. So that means we can replace this expression up here with this one. Now, this doesn't seem like much of a simplification, but if you take this expression out and you expand it all the way out, you're going to get a lot of terms, and I'm going to leave it for you if you like, or you can just trust me on this, but you can take that expression there, and when you expand it out, you can show that it can be rewritten in the form of the angular momentum vector is equal to a matrix times the angular velocity vector. And what the components in this matrix are, we're going to see in the next slide, but they're going to involve just the mass and the position vectors of the particles in our rigid body. So I'm going to write down this expression then, J is equal to I dot omega, and that is our relationship. That's the relationship between the angular momentum and the angular velocity vector. These two vectors are going to be related by this one matrix called the moment of inertia tensor, which maybe you remember from your undergraduate physics course. But what you know is that because we're doing a matrix multiplication, that means that omega and j are not necessarily aligned with each other. That matrix will then cause whatever, when you multiply times omega, omega may be pointing this direction, j may be pointing in another direction. And that difference between them is determined by this moment of inertia tensor. All right, good. Let's move on. Those moment of inertia tensor elements are given here. And this expression, there's different ways in which you can do this, but I wrote this expression out so that I included the center of mass, because generally you'd like to write the moment of inertia tensor for molecules in, relative to the center of mass. So you pick some coordinate system. It doesn't have to be the center of mass coordinate system, but you pick some coordinate system to draw your molecule in, and then you calculate the center of mass, and then you calculate the position of all the atoms in that coordinate system, and from this calculation, then you'll get the moment of inertia tensor components, all 9 of them. But in practice, actually, you only need to calculate 6 because these elements, the off-diagonal elements, are related by symmetry. So IXY is equal to IYX, so you only need to do this one once. And IYZ is equal to YZY, and IXZ is equal to IZX here. So these guys then are another 3, here's 3, so you need a total of 6 calculations to get the 9 elements. Okay. When this is true, when these guys are equal like this is on a matrix, that means that the matrix is a symmetric matrix or a symmetric tensor. Now, one of the properties of a symmetric tensor is that you can always find a coordinate system where that tensor, if you calculate the tensor in a specific coordinate system, you can find a coordinate system where that tensor will be diagonal. So in other words, if I take some given coordinate system, I can find some rotation of the coordinate system or the tensor, however you want to look at it, such that that tensor becomes a diagonal tensor. And in that coordinate system where the tensor is diagonal, then we will have 3 values along the diagonal, and those are going to be called the principal moments of the inertia tensor. Now, the definition that we're going to use is one where we're going to define that coordinate. There are, when you've come up with a coordinate where it's diagonal, it doesn't mean that you've defined the 3 directions uniquely. So what we're going to do is, if we want to make it unique, we're going to define the largest component is going to be here, the smallest component will be here, and the intermediate component will be there. So whenever you find your transformation that gives you a diagonal matrix, you want to redefine what was x, y, and z so that the largest is here, the smallest is here, the largest is there, and the intermediate is there. So that then, once that definition is done, then you've defined what we call the principal axis system for the moment of inertia tensor. So it's not just the diagonal frame, but a diagonal frame with the axes correctly labeled, A, B, and C, to make it the principal axis system with this convention. Okay, and we're using A, B, and C instead of X, Y, and Z because we don't want to get confused. When we're in the principal axis system that's fixed on the rigid body, then we're going to use A, B, and C. But sometimes we'll want to describe what's going on for the rigid body from some space fixed frame while that body's rotating, and then we're going to be using X, Y, and Z. And so to avoid confusion, whenever we're fixed in the body frame, we'll use A, B, C. Whenever we're fixed in a lab or a space frame, we'll use X, Y, and Z. Now, when you're in this principal axis system, which we call PAS, then your moment of inertia tensor will be diagonal. And trying to find that coordinate system can be tricky. When you look at a rigid body, it's hard to know how to orient that rigid body in your coordinate system so that it's going to be diagonal when you do the calculation in that coordinate system. But when you look at the rigid body, you can see some symmetry in the body that might help you identify where the principal axis might lie and then orient your body correctly in the coordinate system. So for example, if you see a 2-fold or higher symmetry axis, then that's definitely going to be a principal axis of the body. So whether we're talking about molecules or a macroscopic body, it's the same. Also, if you see that the 3 principal components of the moment of inertia tensor are equal, then in fact actually any body, any orientation in space can serve as a principal axis system. I'll give you an example here is if I have something that's perfectly spherical like this, then you can set this calculation up, put it in your coordinate system and set up your calculation, and you'll find that it's diagonal no matter how you set this up in your coordinate system because it's spherically symmetric. Similarly, if two principal components are equal, then any two axes that are orthogonal in the plane of those two principal components can serve as a principal axis. So in other words, if you think about this object here, you can see right away that one of the principal components will be along the long axis of the American football here, but perpendicular to that, we're going to have the other two directions, principal axes, and it doesn't really matter if you pick one here and one there, then that's going to work, but because these two will be absolutely equal in terms of their magnitude, any axis that I pick in that plane is going to be a principal axis. So it doesn't really matter when the components are equal that you can pick any in that plane. So if it's spherical, then any orientation will work. But if it's looks something like this, where two of the components are equal, then any orientation in that plane will work too. Okay. Now, a few other points I want to make here, and one is that, remember, for a freely rotating object, if there's no external torque applied, the total angular momentum has to remain constant, meaning dj dt is going to be equal to 0. So if that's true, and the object is rotating freely and is spinning about a constant omega, so say we have an angular velocity vector, you can see the object is spinning with an angular velocity vector that's not changing, then that omega must be pointing along a principal axis system if it's not changing in time. So in other words, J can't be changing and J has to be constant, and if omega is not changing, then they have to be aligned with each other. So that means that J is aligned with omega, omega has to be pointing along a principal axis system. Now, conversely, if it's a freely rotating object and omega is not aligned with J, well, then J can't be moving. So if J is constant, then omega has to move with time in order to maintain J in the same direction all the time. So if they're not aligned, then omega has to become time dependent in order for J to be time independent for a freely rotating object. And then a couple other quick points here is that when we're in the body fixed frame, we're going to define a moment of inertia tensor in the body fixed frame, and that's going to be a time independent quantity. But when you view that same moment of inertia tensor from a space fixed frame, well, it's not necessarily going to be time independent. It may be time dependent. Now here's an interesting thing. This is something called the intermediate axis theorem, which tells us that if you have an object where the three principal components are not equal to each other, then if it's freely rotating about the largest component, IC, or the smallest one, then it will just continue to rotate about that axis stably, just like we just saw on the previous slide. But if it's rotating about the intermediate axis, it can't rotate stably about that axis, and it'll keep flipping back and forth between the two different directions. So this is something that's called the tennis racket theorem, or the Ziani-Bekhoff effect, I believe. And I have a video here. Let's see if it plays. And so here we have an object. I guess it's not going to play. Try again. There we go. Here we have an object that was forced to start spinning along its intermediate axis. And so you can see what it's doing. It's trying to spin about the principal axis, but it's the intermediate one, so it's unstable. Here's another view of that video, a little bit slowed down. You can see as it spins out along the intermediate axis, it can't stay stably and it has to flip. So this is something also called the tennis racket theorem, which says that if you try the way you flip a tennis racket, there are certain ways you can do it easily, but other ways if you try to flip it, it always kind of just flies out of control. So you can read up on the internet about that. Now, what we're going to do is we're going to look at calculating a moment of inertia tensor. So we're going to go back to the example we had in Chapter 1 where we calculated the center of mass. Now let's calculate the full moment of inertia tensor for a water molecule in this coordinate system as we laid it out in Chapter 1. So we already worked out what the Cartesian coordinates for all the atoms were. So let's continue with our calculation. We knew from there that the total mass was 18, and then the position was slightly, of the center mass was slightly off x at 0.06, and then y and z were 0. And we placed the molecule in the xz plane, so all of the atoms had 0 for the y component. So if I go to the diagonal moments of inertia components, then you see in this expression here that I already know that the y and z center masses are 0. So that means that this term I won't have to worry about. This guy and this guy are going to be gone too. And then also since it's in the it's in the xz plane, then all these y components aren't going to be needed when I do the calculation. So let's then take this in simplification and go on and do the calculation. So for the xx component, we just need the mass of the hydrogen times z squared plus the mass of the other hydrogen times z squared. It's z squared, and we put in the numbers here, and you see we get this value here for the moment inertia along the xx direction. This is m squared times kilograms, so mass squared times kilograms. And then for yy, we're going to do this calculation here, and we plug in the numbers and we get this number. And then finally for z, we're able to get this quantity here. So taking these together, then we have the xx, yy, and zz, but we also need to get the off-diagonal elements. And I'll let you work out how to simplify these. But what you find out right away is that you just looking at the equations, you'll see that these guys are 0 based on the zeros that we already know in the coordinates in the center of mass. And then for the xz component, you'll find that this guy, you put in the numbers, it actually evaluates to 0 too. So what we've done is we've done our calculation in such a way that we are already diagonal. So we picked the orientation of the water molecule fortuitously in a way that the moment of inertia tensor is already diagonal. Now, we're not done yet because we have to follow the convention. Right now, we've defined this is xx, this is yy, and zz, but we need to identify the largest one is supposed to be c, the smallest one is supposed to be a. So you see that what is xx is actually the intermediate, that's b. What is yy is the largest, that's going to be c. And what is zz is the smallest, and that has to be a. So we have to take our definitions of x, y, and z, and we have to flip them around and label them a, b, and c so that we have the proper ordering here. So now I've reordered them, and remember now that my coordinates, which I originally defined this way, is x and z with y coming out of the board. Actually, I think my right-handed coordinate system, that would be y maybe going into the board. But now what we're going to do is flip to the principal axis system, and now we have put the center of mass at the origin, and now we have A along this direction, B along this direction, and C actually now comes out of the board. All right, so that's it for this video, and in the next video we're going to look at rotational energy of rigid bodies and also classification of molecules.